morning. This question is from Bresnik and Halliday. The question is about finding the acceleration of due to gravity at the pole and equator of the planet. Now, the impact we have to consider is the rotation of the planet about its axis. When a planet rotates about its own axis, the acceleration due to gravity is impacted by the position of the body. So let's draw a diagram to understand the concept and how we will solve this. Okay, so let me draw a simple diagram, and I'll do this very quickly so that we can solve straight away. So this is your planet. Okay, if you have a body which is lying at any point, for example, okay, and let me draw that point. Let the point be at this. Okay, this is the location of the mass. Now we know this is your uh, pole. Okay, so I'm drawing one line from there, and this is your equator. If you join this point from the center of the planet, the axle and the latitude of the body, the position of the body on earth is this, which is lambda. The net gravity which this body has, which when I say gravity, I mean acceleration due to gravity, is given by g is equal to g naught, which is minus r omega square cos square lambda. Okay, now this is the radius of the earth. R is the radius of earth. Omega, if you notice, omega is same everywhere because it's if the body is rotating like this, every point on the planet is moving with the, so this is the speed of rotation, of the planet, and we can easily find it because we are given time periods. And then lambda I have already marked here. This is the acceleration due to gravity when there is no rotation, okay, without rotation. And this is your effective final g because of impact of the rotation. So you have to memorize this and understand this very clearly. Where is lambda marked? This is the position. So effectively the gravity reduces due to the rotational effect of the planet. The second thing which you need to understand is, since lambda can be varying, right? So if lambda is equal to 90 degrees, which means you're at the pole, okay? So lambda is being measured like this, and the lambda goes from here to here. So if lambda is equal to 90 degree, then g is equal to g naught minus r omega square cos square 90 degree, right? So this is equal to g naught. Okay, so at the poles, when I say lambda is equal to 90 degree, we are talking about poles. At the poles, you can see the acceleration due to gravity is back. It is in fact highest. But if you talk about equator, where lambda is equal to 0 at the equator, then G effective, if I write a G effective is equal to G naught minus R omega square cos square 0 is equal to G naught minus R omega square, because cos of 0 is 1. So you can see the acceleration due to gravity at the equator will be minimum. Okay, so this is where you will feel the lightest weight. If you're living in equator, your weight will be least, but if you go to the pole, you will become very heavy because of the rotational effect. Rotational effect is what we are studying. That's all. So let's go back to the question. With the help of this knowledge, we are not doing derivation here. There is a long derivation which can be done with the help of this diagram, where we can show some forces which are acting and use law of parallelogram to draw the resultant of the uh, forces acting on this body, namely the weight and the centrifugal force. If you find the resultant, the final answer you get is this. This is an approximate answer, but a good answer. So you can memorize this formula and understand this formula. Let's go back to our question and see how we can start, answering this with the help of the knowledge we have acquired. So what is very clear is that the acceleration due to gravity at the poles is highest, right? So if I were to write, so these are the points where these points, right? These are the points which are all poles, and G will be highest. Now the distinction is we have to compare here, which is equator here and here, right? So we already know that at the equator it is the lowest. So let me do it for first planet, which the time period is given. So the first planet, if I consider, G effective, okay, will be given by G naught, and it says these are identical uniform, they are identical in size and mass. So G for all the planets is going to be same, minus R omega square, and we are referring to the equator now. So we are doing everything for equator, okay? We are doing everything for the equator, and this is G naught. Okay, so the first planet, if you see G naught, what is the radius? The size is same, so the radius remains the same. Omega is given by 2 pi by t, so 2 pi by 16. Okay, I'm not changing the units, I'm keeping them as is. So this is your G effective for the planet number 1. For the planet number 2, G effective is equal to G naught minus the second planet, the R, and now we know the what is the uh, time period. So G R 2 pi divided by 24 by R square, and third is G effective is equal to G naught minus R 2 pi divided by 48 by whole square. If you see all of these, this quantity will be the largest because the denominator is the smallest. So this number, if we talk about so the way we solve this is, so we know that higher is the time period. Okay, so this is the time period here, right? 48 hours. So this quantity is going to be very small. So this quantity is fixed. So this minus a very small quantity is going to be the highest, right? So this will be the largest one. Okay, so the G for 48 hours at the equator. So G equator of E will be greater than G, okay, G equator at 24 hours, right? So the way this will work is G third planet, okay, so I'm calling this third planet is greater than G second planet is greater than G first planet. Why? Because this quantity is the largest one, divided you will get the smallest quantity. So G naught minus the smallest quantity will give you the largest one. So this is the sequence for gravity at the equators. Now if you consider the poles where lambda is 0, all of these are equal irrespective of the rotation, because lambda is equal to 90 degree for all of them. So G naught is only dependent on mass and radius, right? We understand that G naught on its own is nothing but given by G m by R square, right? G is same, mass is same, R is same. So at the poles it remains same, and therefore if we were to write the sequence, and we also know as a rule now that the acceleration due to gravity at the poles is more, right? So if I were to write this expression in any form and explain it, the way we will write the final answer is like this, right? So we know the acceleration due to gravity of the first at the pole will be equal to acceleration at the second pole. All these are equal, is equal to g3. This is again equal, and now as we have studied, these all will be greater than. So the greatest one will be 48 hours. So what we have written so far is pole, and now what I'm going to write is the equator. So g third equator, because it is 48 hours, denominator is highest, is greater than g second equator is greater than g first equator. I hope this makes sense to you. So this is the way we will write the answer. Very interesting question. And if you can, work on the derivation, it is good. If you don't know the derivation, it is fine. But go through this question very carefully. What is more important is knowledge of mathematics also. So if you see if you divide something by 16 square, for example, I'm referring to the equator. If you divide it by 16 hours, this quantity will be pretty large, right? This quantity will become very large, and therefore this will become the smallest. And this, for the same reason, will become the largest, right? Therefore, this, at the equator point of view, the third, this particular planet will exhibit the highest gravity at the equator. So I hope this helps, and thank you very much for your time. This is the only channel in the world which gives you complete explanation of the solution. We don't believe that giving you a straight answer is beneficial. You don't learn anything. Now you will never forget how to solve these problems, and you can expect such numericals in your examination of AP Physics, SAT Physics, or if you're preparing for any examination across the globe. So thank you very much for your time, and wait for the next video.